Okay, we're live. Hey, welcome everyone. This is Amit here. We're on week 2 of the office hours on the data science course in SlideRule. And as usual, we have me and we have Alessandro. Hey, Alessandro.
Hello.
How's the week been for you?
Oh, good. I got to have my second round of mentor calls. A
Mm-hmm.
lot of fun. It's good seeing how things are progressing and
Mm-hmm.
the kinds of questions that people have got.
Good, good. So I think Monique tells us a lot of people are still at the kind of probability and stats part of the curriculum, and maybe would be finishing that and transitioning to kind of R and getting started with EDA. So I feel so I think what I wanted to do in the office hour is maybe take it kind of 4 chunks. Obviously, people are free to post questions as we talk, and we'll kind of weave them into the narrative. We'll kind of start with one of the questions which comes quite often. Why stats, and what's the difference between stats and data mining, and kind of that high-level question. And we'll try and answer that. Then go into how do you start getting into the second module, which is EDA and R, and from there probably deep dive to some of the specific questions around what techniques in R and what clustering, and some of the couple of pointed questions people have asked both on a technique side as well as on the application side in how do you do this when you are doing web analytics or A/B testing and so on. And then we'll kind of end with and go back up and say, what does it take to become a good data scientist? To circle back and say, why we think some of the good skills are not only techniques, but maybe something else like curiosity. So we'll come back and kind of talk about that. So that's what I thought. And yeah, so anybody who wants to ask questions, you can put it in the chat. They can put it on the post that's been pinned on the top, and people are also free to join in. We can take at least 7 more people. So if anybody wants to come on and ask a question, just let us know, and Monique will put your mic on, and you can be interactive. We can talk. Sounds good.
Sounds
Okay,
good to me.
so so Alessandra, let's start with the question that keeps coming back, and it's a question that I also face a lot of time when I teach. Is is this stuff that we're talking in data science really something new, or is this just stats that has been repackaged and made nicer for this current environment? And how do we kind of how do you thread the needle between statistical modeling on one end, and kind of the new data mining and data techniques driven on the other end of the spectrum. And I posted something on the chat earlier today, kind of to explain and to predict. But where do you see your kind of take on this, these two ends of the spectrum, and how do you bring them together, or should we keep them separate? And this question I think, will keep coming in every office hour, I guess.
Yeah, I'm sure it will, in one form or another. Um, so this is definitely a question that there's some amount of opinion on. My answer to this question may be somewhat different from yours or from Vincent's, for that matter. I'm referring to, of course, Vincent Granville, who wrote an article, "Data Science Without Statistics is Possible, Even Desirable."
Right.
I'd like to talk about that article in a minute, but first, just to kind of answer the question in broad terms. So for me, I see data sciences in some ways different, in some ways just rebranding. So I'd say that everything, well, a lot of things that matter in statistics matter in data science. I don't see them as very separate at core. The big difference that I see is where big data comes in and data engineering comes in. How that changes the way that you approach problems.
Mm-hmm.
So I think the big criticism of traditional statistics is that it was developed at a time when there weren't many computers, and you also had very limited amounts of data.
Right.
Every data point was painstakingly gathered.
Yeah.
And so in order to come to any conclusions, people had to come up with a lot of sort of mathematical tricks to make it so that you could kind of infer from a very limited amount of data to the rest of the population.
Right.
So Fisher was kind of the biggest genius in this regard, and he developed a lot of these models that we still use today.
Right. Yeah.
But there's the argument that a lot of this stuff that was developed in the early 20th century and before is no longer needed. We no longer need to, in theory, we no longer need to fit our data to a normal distribution, because we can do things like permutation analysis, where you just you take the data that's there and you try 1,000 or as many different kinds of possible realities,
right?
And see how the data matches up against that.
Right.
So yeah, I think that there's definitely the whole approach. Well, statistics as a field itself is changing, totally separate from data science.
Right.
If you look at how the field is changing, the way in which statistics is being taught in schools now is changing to a more of a simulation-based approach.
Yeah.
Which makes sense, because everybody's got a computer now.
Yeah.
So I think that the things that don't change in my mind is the way of learning how to reason under uncertainty, quantitative reasoning under uncertainty.
Right.
And that requires kind of a more probabilistic way of approaching things, looking at things in terms of different hypotheticals and testing different possibilities. And that kind of way of approaching the problem, I think that's timeless. Though the methods themselves are gradually getting updated, and we're able to do things that we couldn't have done.
So I think it's also kind of on a continuum, right? So what worked for small samples and maybe a more frequentist approach, as they call it, and trying to fit normal curves and linear regressions. As we get on a larger data sets and we move to these bigger problems, we may not need to apply those same kind of tricks, but we may move further up the continuum, right? The other kind of perspective I got when I attended a talk by Galit Shimuli, and I think posted one of her papers, which was to explain or to predict. So, a bulk of stats, and even especially in social sciences domain, but most of everything is social science driven, was to explain. So we would try and build a causal model to explain a theory that we have, and to test the theory out, we will collect the data and do the analysis and prove the theory, right? And that would require us to do, because of limited, the challenges of collecting data, sampling, all those kind of things, model fitting, inferences. So the idea was how good the model fits, what's the inference, is it really fitting well to the theory that we have, that we've come up to explain what's happening, right? And that is one paradigm. And the other paradigm, which is now, is we really want to predict. We want to predict what is happening. And when we want to predict something that's happening, the whole thinking changes. You may not use that statistical approach that worked for explanation. You're easy with unclean data or less clean data. You don't want to make, because you're not trying to explain the phenomena. You're just trying to say this. I want to come up with a model that is better at predicting. And if I add more bias, I add more variance to it, I may actually get more nuances to it. I may get actually more predictive power out of that. So a simpler model may have been better to explain the theory, because I can't keep 25 variables in my mind. But when I try to predict, I'm happy to throw even 25, 50 variables into the model as long as each addition of model, helps make predictions better, right? And so there was this kind of two different approaches to stats, which I found very interesting, or thinking. So the kind of the classical stats approach to explaining and kind of coming up with theories or causal explanations, and the idea is the other is prediction. And I think both of them are needed in cases, and they're not ideally two separate. We use explanatory models to predict. We also sometimes use predictive models to build some intuition about what's happening underlying it. But a lot of these machine learning algorithms and at some point become so complex or sophisticated that they don't have too much explanatory power, but they may have far better predictive power. And I think that is one of maybe more a theoretical look at the differences, but it's also one way to think about why that's changing. And I think you need to understand what your problem is, right? So if you're trying to build a model theory about the world, then maybe explanation may work, and which is what I guess a lot of research and science goes to. In business and all, maybe people are happy to have far more predictive models, and so it's happy if I can figure out by doing if I can figure out this, the person is more likely to buy that product, and I really don't care whether adding another variable will make it better or not. So that was another interesting perspective that I found, and it's good. I mean, it is another thing to keep in mind.
Yeah, I think that sounds about right, and you might think of that as being the main difference when people talk about statistics versus machine learning.
Mm-hmm.
There's a lot of this mathematically. There's a lot of the same kind of stuff going on,
Mm-hmm.
but most statisticians are typically thinking in terms of explanation,
Mm-hmm.
and prediction is maybe good to have, but is sort of second on the priority list.
Right.
Whereas with machine learning, it's the other way around.
Yeah.
I personally like to have my cake and eat it too, if possible, and it's not always possible. I mean,
Yeah.
but the ideal in my mind is to get both. Is to have
Mm-hmm.
a model that is that you can understand, that you can take it apart and you can say okay, this is what's going on,
Mm-hmm.
and it also has good predictive power.
Mm-hmm.
But as you say, that may not really, there may be a trade-off. If you're having to deal with 25 variables, especially if you're dealing with interactions,
Right.
trying to come up with a theoretical explanation of why that's happening may be just too much to ask.
Yeah.
But it might be a real effect, and this is one of the things where it gets kind of interesting, where you can have machines that can actually figure things out that are more difficult than what a human could figure out.
Mm-hmm.
So you have cases where deep learning is of course the most exciting development in this regard, where you have cases of deep learning algorithms learning to distinguish things better than humans even can,
Right.
by discovering their own features, and really kind of fascinating stuff.
Mm-hmm.
But I would add one thing, which is that I found that I've actually done quite a bit of explanatory analysis
Mm-hmm.
in the corporate world, because I mean, it really just depends on what the question is, but a lot of times the question will be, how can we, drive up retention? Okay,
Mm-hmm.
well, the first thing is to find something that's a predictor of retention.
Right.
But you don't just want to have a predictor of retention that's some black box thing. You want to have
Mm-hmm.
something that you can actually manipulate, and maybe try to deal with develop some feature that would try to maximize this
Correct.
predictor of.
Mm-hmm.
And then of course you get into the whole correlation causation problem, but maybe that's a later talk.
Yeah, that's man. I even in my background, I think we were much more on the explanatory side in consulting, because business problems are even more complex, and data is even I wouldn't say too big. I mean, there is more and more data, but it's still it's more patchy, and you have many more variables that you need to actually collect by hand, and you do much more of modeling, very simple modeling, but but at one level you're trying to explain, but it's not only explanation that you do. Then at some point you're trying to also predict or at least suggest a solution which goes in the direction of one prescription. And to come to prescription, I think you end up doing all of it. You do descriptive stats to describe what's happening. You do explanatory stats or modeling, and you also do some amount of prediction. And you may use the same model, you may use different models to do that, but at the end you then come back and prescribe something. And yeah, you're right. I think to even in business, to prescribe something, you need to at some level build some intuition about what's happening to them through the model, and explain what's happening, and then also do some prediction saying, okay, now this would probably help you do something differently, and that would be the result. So no, fair point. I think fair point that it's not either or. I think we are all on the spectrum, and we want to probably have good explanatory models to build intuition and good predictive models to suggest some paths that we can go down on. Good. So stats, machine learning, I think we'll keep coming back to this question. Correlation, causation, maybe will come as as more people go deeper into this. So one of the questions that I think the people would be right now as they transition from learning about this basic stats to starting to get into this EDA, exploratory data analysis, and start to get to use R, right, to kind of start to do that. So what would be your kind of so let me so if you had to give somebody advice on start to use R, right? So how do you what would be that one thing, or a couple of things that you'll say, don't be scared is probably one, but after that after that, what would you say, how to get more comfortable with R?
The command line is your friend. Yeah, I think people who maybe are used to using GUIs and haven't done a lot with command line interfaces might be intimidated by that at first. But I think you'll quickly find, if you are in that camp, that that it's worth it. That the hardest part there, especially when you're learning it for the first time, is with a GUI you can kind of poke around and just discover things. Whereas when you have to type it in, you have to look it up. You have to have some other resource guiding you to tell you what to do. And that's maybe frustrating. But the upshot of it all is that you have this limitless flexibility that is very difficult to achieve with the GUI. The way that R is it has one universal format, and so you can easily chain functions together, or apply the output of one function as input into another function. Right. Which just makes working with this stuff so much easier. And once you learn what it is that you're doing, you can do things so much faster than you could if you were trying to do it in Excel or something like that.
Right. Yeah.
And yeah, I think that one of the things that I love about R is that as a language, it is designed to do statistics, and so you have all these very easy ways of exploring your data, and it will give you when you do a simple correlation test, and it will not only tell you the correlation coefficient and the p-value, but it'll also tell you all these other things. Maybe more things than you actually know what to do with. But but it's nice that it really kind of gives you a lot of information about what's going on, and and those can also kind of lead to further questions. So maybe you discover something through one analysis that kind of as a side effect it tells you something else that you didn't think to look at, and you start looking at that. And then, of course, the plotting is a big deal, which we talked about a bit last week. But I don't know if you want to say anything about that.
Yeah. So my experience was the first time I started to learn R, and I had just R, and I kind of poked around a little bit and then gave up very quickly. I mean, my first experience wasn't really that positive. And then I came across RStudio actually, and once I start, I mean, it is not really a GUI. It is a GUI to some extent, but it's not really a GUI that use some people who use SPSS or Stat, uh, to that level, or Excel, right? But once I got into RStudio and I could see, at least a couple of windows, I could see the data. I could actually see scripting. I could see console, and I could also do much more, like do my documentation and the presentation and that. I think that kind of changed my perception of R just from a ease of use. So I think, and I think in the Udacity course they do use RStudio, so that's actually good. So you can. I found that very helpful. I mean, there are many people who may find just the base R as kind of good enough to go, really nice to get into. And then you're right. I mean, once you start to see how just you can take one function and feed it into the other, and you start to see these things linking together, then it just changes. Like you can't go back to some of the other tools where you have to do all this manually. I mean, even for simple stuff like Excel and all, it would be kind of it is cumbersome. And as long as you have the data that kind of doesn't want you to do too much modeling, not too much kind of uh, you know. It is probably very good to kind of get into R. So I think the payoff is really high once you get into it. So don't be scared. Just deep dive into it and kind of get into it. What about EDA? So, trying to learn EDA, and I think there was one question which to me wasn't fully clear, different EDA classifications, but by Santosh. But even before that, like, what is EDA for you? Like, when you start doing EDA and using R and combining the two, how do you go about it? Like, what would be what would be the first things you do to kind of start poking around with the data, just on a looking at it perspective?
Well, histograms. I'm a big fan of histograms.
Right.
Although the caveat with histograms is, you got to play with your bin size, because if sometimes you end up hitting upon a bin size which might create some artifacts that can kind of throw you off. They can make things, can create illusions. But yeah, no, I'm a big fan of histograms, especially because they, well, I mean, they show the shape of the data, right? That's the whole point. And they are they don't really assume very much about the data. Compared to like box plots, which I also like box plots, but the thing about box plots is, a box plot could be, if you're dealing with data that's bimodal, a box plot is not going to show you that to you.
Yeah.
Whereas that will be, really obvious when you do a histogram. Then of course there are variations. There's violin plots, which are kind of like, which is like the love child of a histogram and a box plot. And they're kind of nice, and they're pretty. Yeah, so I do that, and when I make these box plots, I mean not box plots, well box plots too, but when I make histograms or any of these plots, I'll often play with the axes, try to plot it in a log scale or a square root scale, just to sort of see how things shift around, because a lot of times we're dealing with data that's not normally distributed, that's probably has some kind of log or exponential distribution or something like that. Right. And so when you plot it and you see something that looks like an L, trying to draw it with my finger. Well, it's not that there's no data there. It's just that you've got this very, very strong skew. And if you try plotting it with on a log scale or a square root scale, you might see something a bit more interesting.
Right. So I think one of the things that the course starts with is exploring one variable, and I think what you've given is probably kind of the best hints to go down that path, right? So when you're exploring single variables, figuring out what is the plot for that, so histograms or violin plots or box plots, understanding what works for them. What are the things that come out of that? What are the things that don't come out of from each one of them? Scale manipulation also is really, really, really nice. I think one of the library that they use there, so in R, so base R is really good. So graphics is pretty fast, and it will give you lots of things. But I think in that course they'll move to ggplot2 pretty quickly. And one of the advantage with ggplot2 is when you're doing histograms is that it starts with a default bin. I mean, which is I think 30. So it does 30 bins. But then you have to play with the bin, and that's, I think, very good advice to anyone starting with these single variables. Play with the bins and start to see how that changes. And at some point you'll start to get a hang of how to do that. And once you start doing that, and you start to see the patterns, I think, and that's the other thing you need to work on, because seeing, like any other skill, is an acquired skill. I kind of give this example of a radiologist looking at an X-ray, and we can keep looking at the X-ray for a long time and have no clue why the X-ray is telling him that I have a ligament break here, or I have a fracture here. But the X-ray, the radiologist can figure it out very quickly, and it's because he's looked at many of them and he's built some intuition around it. And I think just getting started with all the variables, looking at the univariate analysis, plotting the histograms, looking at it, doing the scale manipulations, like you said, log, exponential, to start to see what happens, then you start to get some intuition around the data. And that's what we're trying to do with EDA. We're trying to get some intuition around the shape of the data, what possibly could be, and to some extent build hypotheses around what we should be doing next. So if you don't know enough about the domain, if you don't know enough about this situation, then looking at the data, just the shape of the data, the portrait of the data, as I call it, is a very powerful way to build some intuition around that. And think of this as, yes, we're doing stats, and we're trying to we're trying to be quantitative about it, but at one level you're just trying to get a better sense of the data, and that's what you're doing by using your pattern identification skills in visualization, and to start to get to understand the intuition around it. So yeah, deep dive into it, use ggplot, get to know what bins to use, what scale manipulations to use, and I think that would be a good start, right? That would be a good start. And then maybe next week we can talk more about, as we move from univariate to two-variate, or analysis, what could be. So as we move from 1 to 2 variables, then what would be possibly other things that people can do, or also multiple variables, where then it becomes even more challenging as you go from 1 to 2 to kind of.
When you get to 4, things get really interesting.
Yeah.
So yeah, actually, I want to comment a little bit on the ggplot as well. So your experience of R is my experience with ggplot. When I first decided to try to learn ggplot, I just was like, what the hell is this? This is not right. This is very strange.
Yeah.
Because, and the reason for that is that, and maybe it was just because I got so used to using the built-in Python, R library, plotting library. And it's a very different approach. But in the end, it's definitely one of those things where it's worth it, because ggplot is really, the GG stands for Grammar of Graphics, and it's really brilliantly designed in a way that the way in which you create your plot is it says something about what you're doing with the data. It's not arbitrary. Every decision that was made in the way in which you layer the function calls in ggplot is, says something about how you are revealing certain aspects of your data, what you are showing. And it's got some really, really great stuff for doing multivariable visualization, where you can do things like heat maps and all kinds of other kind of interesting things to reveal 3 and 4 dimensions right there in your plot and the facet grid thing and so I mean I remember about a year ago I advised an intern to actually go through the ggplot list of functions and actually just like use all of them one at a time, which turned out to be have some side effects where she did that, but she wasn't necessarily totally aware of what she was doing when she ran each function. And so she came up with some very funny charts that didn't really make any sense. Because, of course, ggplot doesn't care. You tell it to plot this variable against that variable.
Correct,
It's not going to correct you and say, oh, no, this variable is counts, and this other variable are actually, each row is an actual thing. So you do have to be careful. Make sure that when you do play around, that what you come up with actually you can explain it to somebody. And if you can't, that's a good time to talk to your mentor. But I think that there's just just going through that list of functions can give you a good sense of not just of what ggplot is capable of, but also just you'll kind of discover ways of thinking about data, ways of exploring data.
Yeah, I think that I mean, it's right there. I mean, I actually, so in my case, since I was coming from a NarrativeViz background or trying to do more visualization, for me, grammar of graphics was kind of amazing. I mean, and to find a tool which implements the grammar of graphics makes everything so easy. So I actually probably learned the ggplot first, then the base graphics, to be honest. When I look at base graphics and say, okay, why are they not defining the aesthetics here? And how are we defining the colors? And so for me, it was the other way around, and I found it easy. And and if you want to create charts that have no names, and at some point you will come down to the point where you will be creating ways of visualizing stuff which have no names. So there won't be the the box plots, the histograms. There'll be charts which have no names. And when you want to do charts which have no names, then you need to use the grammar, because the grammar gives you unlimited ability to create charts. And I think that's kind of the upside. So I'm going to post a link in the kind of just for people who are wondering what this grammar stuff all is that we're talking about. Is there is there really is there something about it, or are we just making it up? No, we're not making it up. There is a grammar to doing visualization, and there is and if you can understand the grammar a little bit, it helps. So I'm going to post a slide share on kind of like a simplified grammar of graphics. And it's like taking you to create a humble chart, and just with a very simple data ID, you understand. Once you understand the grammar, you can construct unlimited number of visualizations out of that, and that's the real power of ggplot. So it all pays off, is all I can say. If you invest right now in R, you invest a little bit in learning ggplot, it'll definitely pay off. Not only in EDA, at some point even in developing the charts for communication, and you can do lots of stuff in making the axis, changing everything. You can basically make it into a chart that looks as good as you want later on by playing around with these labels and everything. So it has amazing flexibility, and it'll pay off.
Yeah, another nice thing about ggplot is it was designed with certain aesthetic considerations in mind. Unlike the basic plot library, or unlike matplotlib, or unlike pretty much anything else that I've seen, except for a few things more recently that have been copying ggplot, frankly. That if you just make a plot, it will look good. It will look like something that you want to put in your PowerPoint presentation, or it's
yeah. Okay, so I mean, feel free to come back with more questions around that, or to your mentor, or even post it here, and we'll kind of try and address some of that. So yeah, so maybe next week we'll talk a little more about what do you do for 2 variables and multiple variables, and kind of take it from there and see what else people have in mind. I think I'm going to go to some of these questions around I think one is kind of from now we're kind of the business questions, or kind of application questions, right? So one of the questions is really around web. I mean, a lot of data, that big data or data gets generated, is because you and I and everybody else is spending so much time on this computer and clicking away at any website, and anything, buying stuff online, and and everybody's trying to get us to do more of that. And that's where I understand this A/B testing and web analytics and all starts to come into play. So, and I think there are a couple of questions around that, around saying, so what is A/B testing? I mean, when people say A/B testing, I mean, can you link that back to how we should be thinking from a data science perspective? So what it is for people who don't understand A/B testing, and how do you link it back to what are we doing in part of this data science? What is the kind of underlying technique that we're trying to use there? Control versus sample, or however you want to define it. And then kind of the question is really around what are the techniques that would make it better to do that, like to think about that. And I think techniques, I don't even want techniques, just explain what the intuition behind A/B testing is, and how we can start to think about those kind of problems, and where can that analogy be applied to even different problems, right, where we're trying to do something similar, right, in different domains.
So I'll start with the a kind of a famous example of A/B testing, just to kind of set the stage. And this was during the Obama campaign back in 2008, or I guess even 2007. Anyway, so the this was probably the first big time that data science, which at that point was still a fairly new concept, was used for electioneering. And so there was the big thing that all electricians are trying to do is get people to donate money to them.
Right.
And vote for them, obviously, but sometimes the money seems more important.
That's the first thing you want them to then vote, yes.
Right. Yeah. So they were looking at ways to get to motivate people to donate to them, and they had a bunch of different candidate images. They had videos on the homepage, some which were very lovingly crafted by professional filmmakers and everything. And of course, a lot of people thought it's going to be the high production value video that really engages people and really gets people to want to contribute.
Right.
But somebody said, well, maybe we should actually look at this. Maybe we should actually see what the best option is. Not just pick what we think is the best, but actually find out.
Test it.
Actually test it. So they developed multiple versions of the web page. Basically, every time you went to that page, you'd randomly either see the video or you'd see one or another of the different images. And then there's a contribute button. And so the question was, how many people actually click the contribute button? Or I'm not sure if it was the test to see if you clicked or if you actually went through and actually made the contribution. But either way. And much to everybody's surprise, the video actually did very poorly. And the theory, and this theory was explained. People came up with the theory afterwards.
Yeah.
After they saw the data, they saw the video did horribly. It was like, oh, well, it's because the video takes too long. Nobody wants to sit and wait for a video to buffer. Especially, even if they have a fast connection, and of course most people don't have that fast of a connection. So they come to a page where there's like a buffering video, and they're like, oh, screw this, I'm going somewhere else.
Moving on, yeah.
So that was sort of fairly high-profile example of A/B testing at work.
Mm-hmm.
Now, there's...
So here, just a question. Again, linking back to what we were talking at the start of the session, you're not trying to explain why something is better or not, right? You're just trying to predict that it looks like the photo works better than the video, right? And the explanation
the explanation came afterwards.
Came afterwards, right? So you're just trying to say, okay, two options, and it looks like this works better, right? And I keep and okay.
And if we were scientists and not politicians, that might lead to the question of well, okay, now we have a hypothesis that videos don't do as well, and so we might create an experiment to test that hypothesis.
Right.
Of course, that their motivation was not to find truth. Their motivation was to get money. So they didn't really, they had this explanation that was good enough for them. It wasn't worth the time or energy to actually see if that was true. So that's I think that was where Optimizely actually came from. Was the people who put that together created Optimizely.
Mm-hmm.
Of course, they didn't invent A/B testing. It's just, as I said, the kind of a high-profile version of it. I mean, one could say that A/B testing goes back to the 19th century when the brewers at Guinness were trying different formulas to see what what sold better. And I mean, probably even older than that. But but now we have this sort of very easy automated way of doing things with the web, where you can you can create 100 different versions of a web page in a few minutes and see what happens. And those 100 different versions may be experienced by thousands of people.
Mm-hmm. So this technique is not really new, right? I mean, I remember working for Cadbury's, and every day they would have different different flavorings for the chocolate eclairs, and you'd go down, and every day people will eat two of them and say which one is better, right? So we're doing A/B testing in there. Gillette, everybody comes in and shaves in the morning and tests the kind of which razor is better. So the technique is basically have two options which are identical in pretty much everything other than whatever one or two of those differences. And I think in economics they also do it. They call it randomized control testing, or RCT. So okay, so much applied, used everywhere, now maybe in vogue because we have many people coming to our website and clicking. So there's more easy to generate data around this A/B testing, right? We can do this very fast, and we can do this rapidly than we could have done it anywhere else, where you actually literally have to go and make another eclairs, right? You can't really just can't put a photo of another eclairs. You have to formulate the new version and then test it, right? So it would take longer. Now, showing somebody a different ad is as easy as maybe a change in the model. Okay, what technique goes behind it then? I mean, what's the statistical thing that we're trying to do?
Well, so this is where things kind of can get surprisingly tricky for such a simple thing. So one question that comes up sometimes is, well, how many, can we just do A/B testing, or can we try many different options? Can we try, 5 different, photos? Okay, well that's fine. So we're trying 5 different photos. Well, now let's see. Maybe we want to try 5 different photos. And we also want to change the text on the button. Maybe the button should say "contribute," or maybe the text should say "click here," or And so now now you've got 2 different variables. Well, now you have to be careful, because if somebody clicks, how do you know if it was because of the text of the button or because of the photo?
Right.
So you now need to do what basically have every combination of both variables in order to see what's going on.
Right.
And so now, if you've got 5 photos and 3 versions of the button text, you've got 15 different experiments that you're essentially running, or 15 different treatments. One experiment.
Yeah.
But that's fine. You've got thousands of visitors all the time. So then the question is, when do I get to know when do I get to know which one's best?
Mm-hmm.
This is the question that every PM wants to know as quickly as they possibly can, so they can move on to the next thing.
Right.
And there is a inordinate desire to peak. So to look at the numbers before the experiment is really complete. And this is very dangerous because basically you can have there's this concept called regression towards the mean. And maybe later on I can go into more detail on that, or perhaps you remember it from if it was covered in the probability section.
Right.
So regression towards the mean, basically what that means is if you do one test, there's a very good chance that you will get an outlier result. If you roll, if you go to the casino, it's quite possible that you will, win at roulette. It's not terribly likely, but it's not impossible either.
Correct.
And so if you play roulette once and you win, you might think, I'm a winner. I will always win roulette. Right. That's, when, of course, that's not going to happen. I'm sorry to break it to you. You're not going to win roulette every single time. Right. And if you play enough times, you'll see that. You'll see that, oh, on average, I win 1 out of every 33 or whatever times. So if you look too early, you might get a very skewed version of reality where it looks like there's one clear winner or one clear loser, when in fact you really don't have enough data yet.
Right. So you decide how long the campaign will run, the experiment will run before you so you say if it has to get so many data points before we will make any decision, right? So ensure that you're getting more a mean rather than outlier. Okay.
Right. So this is done through a power analysis.
Okay.
So you say, I want this much confidence, and I expect this much of a difference between the two. So I want to make sure that, if I'm going to commit to putting something up there, I want to make sure that I get at least a 10% lift or something like that. Right. And I want to be sure within, 1% or 0.1% error. Right. And what I mean by that error, that's the p-value, the dreaded p-value. And the p-value is your likelihood of getting basically a false positive. So basically, of thinking that you've got a result, but you don't actually have a result.
So I'd say it's clear that many things that you need to keep in mind. How you design the experiment, so that the options are all represented. In classical stats, we used to do conjoint analysis as one way of synthetically determining some of these experiments. But so now you have ability to actually, and also then a priori decide how long will it run, what is my parameter for making those decisions, because otherwise it's very easy to get biased later on and either look at it earlier or believe, oh, this is good enough, right? So you decide those parameters around confidence level, how much uplift or whatever word you want to use you need before you will actually say that the experiment has been successful or has been inconclusive, right?
Right, and another thing I want to add is the importance of when to do an A/B test properly, you need to randomize the treatments across your population, and it needs to be, ideally each individual user will get the same treatment consistently, but the important thing is that you don't have, you're not going to correlate some compound with a treatment. So, for example, one thing that I had to explain to a manager over and over again was why you couldn't just test before and after product release. Does the new do you get more users or more money or whatever after a release? Right. To say, okay, well, this feature made us so much more money. I mean, you can't. Nothing's going to stop you from doing that. But the big problem is that say same time you release, you also release a press. You give out a press release saying, hey, we've got a new version. And that gets people's attention, and suddenly people come and they download the app, or they go to the website or whatever. And so you see this huge uptick, and you say, oh, the feature is really great. Actually, it had nothing to do with the feature at all. It was entirely because of media.
Right.
So you need to, to do it right, you need to make sure that the two groups that are getting the two treatments, that they really are, it's totally random, they're getting the same thing at the same time, there's nothing about them that's different, there's nothing about the server that's different. You need to make sure it's not like you're going to have one server with treatment A and one server with treatment B, because if the second server starts acting slow, then it's going to look like treatment B sucks, but it's not treatment B, it's just that the server has a problem. All these little things, but a lot of times people, if you're not approaching it right, you can make these kind of rookie mistakes that can really kind of screw you up.
Right. So even though now we have access to do these experiments so much faster, we still need to have the basics correct, right? I mean, this is what you would want basics to be correct, even when you do it, not on the web but physically. That the population is random and there are no other kind of variables that are playing into the game.
So the nice thing is that there's a ton of libraries that are already out there. If you're doing web stuff, Optimizely is very easy to use. Okay. Facebook released their A/B test framework, which if you're a Python shop, using that, plugging that into your system is fairly simple, and it was very I saw how they made it. It makes a lot of sense. It's I would endorse using that. I've never used it myself, but I've seen the logic behind it, so it looks sound. So you might want to do that rather than trying to roll your own, because you might leverage the expertise that's been hard won.
Yeah, build on the shoulders of someone else. There was another question kind of linked to that, because you kind of said on the confidence interval, and I think, Alessandro, you said you shared the confidence interval visualization, right? And the question was, if the 95% confidence is created from a sample of the population, why should the confidence interval coverage be less than 95%? So can you just kind of talk a little bit about the confidence interval and how does it come into play, and then kind of talk about how we should be thinking about that, right? How should we think?
So so this is one of those things where it's kind of it's a little bit counterintuitive, and it kind of requires your brain to kind of you're trying to sort of turning reality on its head. So the thing about a confidence interval is okay, so there's a 95% chance that the mean is within this range. Assuming it's 95% confidence. Okay, what does that mean? That means that basically, if you were to do this experiment 100 times, right, you would get 100 different values, 100 different results, 100 different spreads, and 95% of the time, the true mean, which you will never actually know unless you go out and experiment on every single individual in the population. Yeah. The true mean will be somewhere in that range, which also means that 5% of the time, 5% of the time it won't be. So what this visualization does is it shows every time a dot and line appear, it's like that's a different version of reality, a different experiment that you've done. Right. And every time the line is red, that's when you did the experiment perfectly right. Nothing went wrong, but it's just by chance you get that weird outlier result. Okay. So I'm not sure if that answers the question. Yeah. So you don't. So I guess one of the things that I want to say about that is, I guess the dotted line in the middle where you have the mean is 0. You don't actually. That's the bit that you don't actually know. So I guess the question asks, what if something about when would CI coverage be less than 95%? Correct. Well, the thing is that you don't. So the confidence interval you set whatever the confidence interval you want, and so maybe if the question is, when would you use a narrower confidence interval, like maybe you want a 50% confidence interval, then you're basically, so if you're going to do a 50% confidence interval, you would have more precision but less accuracy. So you'd have a narrower band, but there's a 50-50 chance that it's outside of that band.
Right. The other thing you could do is play with the sample sizes, right? I mean, sample sizes also play a part in kind of playing with this, right? So if you are using a very small sample versus using big sample, what does that then happen?
Right. So every distribution has a certain variance, and also just we're assuming everything's normally distributed, which of course in reality things aren't. But for the sake of making this conversation easier, we'll assume that everything's normally distributed, and everything has a normal distribution. And so there's a variance that everything has. So if you think about like height, everybody there's a mean height that every male in the world is, and every female is a slightly different mean. Right. And then there's a variance around that, and it's fairly, it's a nice bell curve kind of thing. Some people are taller, some people are shorter. Now, when you do your sample, so say I want to take 100 men and measure their heights, and I've taken these men from all around the world, so it's a simple random sample, and I'm going to use this to figure out what is the mean of all men in the world. What's the mean height of all men in the world? Right. So what I'm going to get is I'm going to get the mean of my sample, and then I'm going to get a standard error, which is this is where it gets kind of nice, because what it turns out is that the standard error is the standard deviation of the population. So it's the variance of it's estimated standard deviation. It's not the real standard deviation. It's the estimated standard deviation of the entire population divided by the square root of n, where n is the number of people. So divided by 10, since I've got 100 people. Square root of 100 is 10. So the standard error is my error bands around which I can construct my confidence interval of the mean that I'm trying to compute. So if I want to say I want to shrink my confidence interval in half, I want to drop my standard error by half. The standard deviation is going to stay the same because that's just a feature of the population. But if I quadruple my n, so if I go from 100 to 400, then my square root of n is 20. So I've now dividing my standard deviation by 20 instead of 10. So I've dropped my standard deviation by my standard error in half. So I still have a 95% confidence interval, but the width of that confidence interval is now at half as big as it used to be.
Right.
Does that make sense?
Yeah, that makes sense. I mean, that makes sense to me at least. And I think these, so it's great, these visualizations, and there are more of them on that page, talking about correlations and some of them. I think I also earlier today shared some visualizations around, Simpson's paradox and conditional probability and center limit theorem. And I think, again, the idea of these visualizations is, as we were talking last time, to get some intuition around these concepts, right? Because you can keep reading about it, keep talking about it, and then, at some point you need to grok it somehow. And I mean, use whichever works. So if examples work, use those. If these visualizations help you to start seeing that, then, those are also good. I mean, those also make sense to kind of do that. And I would really urge everyone to go through them, and even some of the other ones which look at correlation, and to start to understand some of these statistical concepts. And the more you play with this, easier it'll become, because when the real data comes, it's all it's all more messy and not as simple as this explanations sometimes are.
And I'd also recommend, coming back to the visualizations, because sometimes, maybe when you first look at this confidence interval thing, you're like, looks like some pretty lines. I don't get it. And that's fine. And but maybe down the line, when you start dealing with actual data, you're again exposed to the concept of the confidence interval, and then go back to the visualization and see how these different confidence intervals work, and then kind of So you might bounce, revisit these over and over again.
Yeah.
Because sometimes, a lot of these concepts are pretty counterintuitive, and sometimes it takes, a few times to kind of see the visualization, read more, practice more, come back,
Mm-hmm. Come back to
other
this.
rinse repeat.
Makes sense. I think we're out of time, so I think there are a couple of more questions which go into clustering and.
I did promise to answer the clustering question, although that is kind of a more advanced question, so maybe we should save that for next time.
Yeah, so I think because I'm not sure how many people would already be looking at that.
Yeah, Julian, I'll explain it during our office hour. I mean, our mentor call on Friday.
Yeah. And so I think what would be good, as we kind of close this office hour, is really start to play with some data. So get something that you are really interested in. Find some topic that you're really interested in. Because if these things are not coming from work, find the data that you are really interested in, a topic that you're interested in. It could be Black Friday, it could be anything that you find interesting. Could be some public health related, public data related. There's so much data available these days, and start to do what you're learning in EDA even on that data. Like just put it in R and start to see and visualize it, and you learn so much about it, and then these concepts that you are learning will also start making sense. So, and I think that's one of the things I would kind of like to end on, is really one of the things that makes the difference between learning these concepts and actually becoming a good data science is that you have some curiosity, some drive around finding something out in a set of data. And if you have that curiosity, interest in understanding some data or predicting something, then use that interest to get into these topics, right? Because you can then use that data to, it'll push you to find out and kind of go from there. And I think that would be one of my things to kind of build on. So find something interesting, just start using these techniques, and then plot those single variables, histograms, figure out if you take a sample from that versus the whole population, and then build your own. Understand how the confidence interval comes into play when you change sample sizes, or how, and you'll start to see that it's far more easy to grasp once you do that on your own data set. So I think that's from me. Alessandro, anything from you as we kind of wrap this office hours?
No, I think that's a great recommendation, and yeah, you could even kind of do your own version of the confidence interval thing, without the D3 part. But yeah, just by subsampling from a data set that you already have. So yeah, I think I definitely recommend doing that. Play with your data. Share with, if you come up with something that you think is either cool or is confusing, post it to the group, post it to the community, and see what people say.
Sounds good. Sounds good. So, well, happy hunting, everyone, for those confidence intervals. Happy hunting for those samples and means. And till next week. And I think Monique has put a question around when we do that office hour next week, because I think it falls on on
I think it's
New Year's.
Christmas Eve, and then the one after that is New Year's Eve. So,
yeah.
Please
Please send
vote.
in your votes. Yeah, please send in your votes, and then so the dates would be different, but yeah, if you follow the calendar, you'll get to know when it is, and we'll take it from there. So till next time, whenever it is.
Till next time.
Bye.